So, you want to be an electrician. Let's start with the basics. Quantum physics dictates that a ripple in the electrostatic field causes an electron to form around the atom.
No, that's too much. Let me take it from here.
Oh, fine.
An atom is made of a nucleus with electrons flying around the outside. It's the flow of these electrons through a wire that we call electricity. Now on to how we measure it. If you think of electrons as water in the pipe, the flow of the water is what we call current, and the force behind it is known as voltage. Electrons can flow through anything with enough voltage behind it. For some materials, this voltage is relatively low, so we favour these for wires. These are called conductors.
Like drain people.
Anyway, now that we've explained why we use materials that conduct well, we should probably talk about insulators. Insulators are materials that need a very high voltage to pass a current through, as they don't inherently let electrons flow. Such insulators are rubber, PVC and ceramics, all of which at different times have been used to protect circuits in different ways, which we'll come on to later.
Whoa there, buddy. You've told them all about how electricity works, but not where it comes from.
Good point. Can you take that bit? Just don't overcomplicate it this time.
There are many different ways to generate electricity, such as coal, gas, and nuclear. But all of these do the same process. Harness energy to turn a turbine which spins 50 times a second. We'll get back to that.
What about solar panels?
Ah, good point. These are an exception. While they do generate electricity, they don't spin a turbine. They actually generate a different kind of electricity called DC.
Like Batman?
No, this DC stands for direct current. This means the electrons travel in one direction in the circuit.
We should probably explain what a circuit is.
Oh, I'm sure the people know it comes from the Latin circuitus, which means loop or circle. It's common sense.
No, only you'd know that.
Fine then, you explain it.
A circuit is a complete pathway for electricity to flow. In our case, it flows from the positive side to the negative. On the positive side you have a high potential and the negative side has a low potential. The difference between is what's known as the potential difference, which is commonly known as voltage.
Now look who's overcomplicating.
Right, anyway, back to DC. Most commonly this type of electricity is used to power appliances such as TVs, computers and battery chargers. But to get the DC here, generally it arrives in your house as AC. Do you want to take AC?
I just realised why they're called AC/DC.
Please stay on topic.
AC stands for alternating current. While DC travels in a single direction, AC alternates direction 50 times a second. This is a result of the turbine spinning back at the power station at 50 Hz. Here is a graph of how AC works. It starts at 0 and then moves up to 320 volts, and then back down to minus 320 volts. The average of this, which is known as the root mean square, is 230 volts, also known as mains voltage. But how does it get to your house?
The electricity is transmitted through huge conductors that you see attached to pylons. The power lines are at extremely high voltages because it's easier to transmit high voltage rather than high current, but we won't go into why in this video. When the electricity reaches your street, it's at a way too high a voltage to be worked with, so we use transformers to bring it down.
A transformer is used to step down the higher transmission voltage to a more reasonable mains voltage. How this is achieved is beyond the scope of this video, but what's important to know is that at a transformer there is a big conductive spike driven into the ground that is connected to the neutral. But you wanted to be an electrician, so let's tell you the parts that matter. Since I'm a man of physics, I'll hand you over to my practical friend.
Okay, so in a simple AC circuit there'll only be 3 cables: the line, neutral and CPC. But for now we'll only focus on the first 2. By convention, line, sometimes known as live, should be coloured brown and the neutral should be blue, so that anybody looking at the circuit can identify straight away which one's which. It's possible though that you may see black and red cables. This only means that the circuit was built before we harmonised our colours with the rest of Europe, and all you need to remember is red is line and black is neutral.
I'm so bored. Can we talk about people getting electrocuted?
No, but we can talk about how we stop people getting electrocuted. Earth is probably the best place to start if you want to take this.
I shall. The earth conductor is taken straight from the neutral back at the transformer. Since they're connected, all things that are in contact with earth are at 0 volts. This is the reason you can get a shock just by touching the line conductor. It may not seem like you're completing a circuit, but you are, because the actual ground you're standing on is a path for the electricity to get back to the ground rod. This may sound like a bad thing, and in reality, it makes it much easier to get a shock, but it also makes some key safety devices work too.
Now that we have a safe path for current to flow down when there is a fault, we need a way to detect and switch off the faulty circuit, as it's likely that these cases pull enough current to overheat the cables, potentially causing a fire, and this is where MCBs come in. You've probably seen these at home in your consumer unit. They're devices which are designed to break a circuit when a current higher than their rating passes through them, so if the right one is fitted, it will shut off a faulty current draw, but not the day-to-day demand. Finally, we have protected the circuit from overheating, but if you touched a line conductor, they can still break too slow to save your life. So when people are at high risk, we use RCDs.
RCDs, or residual current devices, are protective devices that your line and your neutral go through. A rule in a circuit is that the current leaving is equal to the current returning. None can be lost. Remember how every piece of metal is connected to Earth? This means that if you should come into contact with anything bearing a potential, and it travels through you down to Earth, then some current has been lost. The RCD works by monitoring the current going out the line and in on the neutral. If it notices some current is missing, then it will turn off in under 30 milliseconds. This is usually quick enough to avoid serious damage. It's worth mentioning that these will only work if you happen to get caught between line and Earth. Nothing can save you if you catch yourself between line and neutral. That's basically all of electricity.
It's a rather grim way to end the video.
Yeah, you're right. Let's put up a picture of a cat.